Namaskar. A very good afternoon to you all. I welcome you to the very first lecture on basics of remote sensing, where I'll be taking you through the principles, what, why, and how of remote sensing, and some physics-based concepts. So let's begin with. So in order to have scientific information of any phenomena or any object, what options we have with us is, number one, either we go to the field, take the instrument, collect the information, and then do the analysis. That is called field measurements or in situ based observations. The other method is without going to the actual phenomena of occurrence or the actual targets, we remotely sense the information and then do the further analysis. So these two information are available. These two types of information modes are available to us: in situ measurements and remotely sensed data. So now coming to what is remote sensing. In situ observations, we all understand. Let's say if I want to take the temperature of your body, I use a thermometer, yes? And the information on temperature of the object can also be taken with the help of infrared cameras, right? So that's a form of remote sensing. So we will discuss and try to answer the questions, the three basic questions on any science: what, why, and how. Now, what is remote sensing? Very simply, it can be put as it is the science and art of obtaining information about three things. That is, one is object, the other is area, and the third is phenomena. Now, the takeaway here is that the information which is to be collected about these three things is to be with the help of a device which is not in physical proximity or physical contact with the same. Okay, so we are going to take information about an object, like, let's say the object of interest is a building, or I'm interested in an area, let's say, where there are multiple features in a field or a city. Phenomena, like something which is happening, rainfall or any kind of disaster. So if I want to get information about object, area, or phenomena without being in physical contact with the same, this is the form of remote sensing. Now, it is both science as well as an art. In fact, it started as an art because it depends on the skill of the interpreter, how well the interpreter interprets the information taken through remote sensing. And it is science, of course, because it is utilizing all the scientific principles and which are further used in bringing out the technologies. Now, I hope we understand what is remote sensing. So it is science and art of obtaining information or gathering information about three things: object, area, or phenomena, without being in physical contact with the same. Next comes to why remote sensing. We are all here today gathered together to understand what is remote sensing, how we can utilize it, and so on, the concepts related with it. But why remote sensing? When you have a thermometer, for example, I stated in the very beginning. So there are certain advantages associated with remote sensing process over in situ measurements. For example, systematic data collection. So you have a systematic pattern of data collection in a fixed row or fixed path, etc., with remote sensing. Whereas if I send 10 people to the ground, 10 different types of errors, 10 different types of sampling might be coming across. Okay, so it brings about objectivity in the information collection. Number two, information about three dimensions of real objects. I hope all of us today are looking at Google Earth, and at many places you have 3D structures available. So this is all possible using remote sensing satellites, which are looking at the stereo dimensions. Then coming to repeatability. Now, repeatability, when I speak about, it is the repeatability in terms of space as well as time. So we can repeat the information over a same area after regular intervals of time. Then comes global coverage, which is possible using remote sensing. In fact, there are satellites which can have a global coverage in a day or two. Then sometimes it is the only solution for inaccessible areas. Let's say if there is a volcano eruption or if there is any disaster, sometimes this is the only solution left with us. And then, of course, the same information can be interpreted differently by different groups of people, different application specialists like water resources, urban studies, or forestry, or geosciences, etc. So same type of information can be extracted and interpreted in different ways by different application groups. But is it all? These are some of the advantages I have listed here. Of course, there are many more. You can yourself look at them. But is it all? Should I throw away the thermometer as I discussed in the very beginning? No. For checking how much correct I am, I have to go to the ground truth or in situ measurements. There are still certain fields, for example, subsurface analysis, where still in situ measurements are more dominantly used. Okay, so of course, in situ measurements are more accurate, but remote sensing has its own advantages, due to which this is being very much popular. And whenever we have some information analyzed through remote sensing, we should always check its accuracy. We should check for its validation using in situ observations. Also, before launching any sensor on board, we have to first calibrate it with respect to ground measurements. So both for calibration as well as for validation purposes, we are still dependent on in situ measurements. In fact, I would put it this way: as long as remote sensing survives, in situ measurements or ground truthing has to survive. So now we have answers to two of the queries, what and why. And now coming to how to make this process happen. That is the remote sensing process. So I have put it in this manner. I hope the cursor is visible to you. Now this is the source. First of all, any target or any piece of information to be coming from any object needs to be given some energy. So if C is the target, if this is the target, let us say this is my object of interest. This object of interest must receive energy from somewhere. Either it is itself the source of energy, or it is illuminated by some source of energy, artificial or natural. In this case, this sun here depicts the natural source of energy, which illuminates all the targets on the earth. So what happens is the energy from the source comes to the target. Part of it is reflected, part of it is transmitted, and part of it is absorbed. Now, if I have a sensor on board on some platform, let's say I have a satellite, which is a combination of a sensor and a platform. This sensor observes this reflected part of energy, okay, records this information, and then later on it disseminates to the ground station whenever it is in line of sight of this antenna. Okay, so this is the information passing on to ground receiving terminal, which is of course a set of several antennas and the associated electronics. Now the information has been collected on the earth. What else to do? We try to free it from some known errors first, because at the data provider side, some types of errors are easily modeled and are known to the data provider. So before the data is given to the user, this raw data is first cleared up for its errors. Okay, so this is called pre-processing, and finally it goes to the application group. So what we see here is we need a source. We need the source of energy releases some energy. So we need some medium of information, that is your electromagnetic radiation. So this electromagnetic radiation reaches the target. Target reflects a portion of energy. This reaches to the sensor, which is attached to the platform. It can be an aircraft-based platform, it can be ground-based platform, or it can be spaceborne platform. Now, after the information is collected here, it is again given to the ground receiving terminal, from where it is pre-processed, and then it can be given to different application groups. Now, for Earth observation, there is a layer of atmosphere which covers the Earth. And the information which is coming through electromagnetic energy is altered because of interaction of this energy with the atmosphere, both while incoming as well as while outgoing. That is, say my target of interest was C, this tree, okay? But the energy interacted with the atmosphere before reaching the target. And again, after the reflection from the target, it has to again pass through the layer of the atmosphere. So again, some interaction will happen with the atmosphere, again, some alteration in the data, and then the data which is reaching here will be altered. So the data which reaches the sensor is having the information both from your actual interest, that is your target, as well as noise or alteration due to atmosphere. Okay, so this is how your remote sensing process will go. Now, there is a possibility, as shown with this dotted double-sided arrow, where the source itself, where what is happening is the source is not A. The source is on the platform itself. It's like when you use your pictures using flash on your mobile camera. So your camera is having is sensing your signals coming from you, but your mobile handset is also having a flash, which is a source which eliminates you first, and then the backscattered or the backward flown energy is recorded by the camera. Similarly, if I can use a source on the platform along with a sensor, so what will be the combination here? Here you will have a platform, you will have a source, and you will have a sensor. So the source will first eliminate the target. Part of it will be backscattered in the direction where the platform is taking the information. This part of energy is sensed by the sensor, which is also again on the same platform, and this type of remote sensing is called active remote sensing. So you see the difference here. The platform was not using any source in the first case with the red solid line, where the source was the natural sun. Okay, the natural source was there, and you are just having a sensor on the platform. In the second case, you also had a source along with the sensor on the platform. So the red one is a form of passive remote sensing, and the blue one is the form of active remote sensing. More details you will study in the next class. Then you will have another instance. For example, here you can see the third dotted line with a single arrow. What do you understand by this? We see that the target itself becomes the source. Okay, how it will happen? Everything in this universe above 0 Kelvin is radiating some part of energy. Why? Because we're all absorbing some form of energy. So according to law of conservation of energy, nothing can be a perfect source or a perfect sink. So what will happen? Depending on the temperature of the object, the amount of energy will be emitted by the body. So these emissions from the targets are captured by the sensor. If the sensor is capable enough, for example, your spy cameras or night imaging cameras, which do not require any illumination on the target. The target itself, due to its body temperature, becomes the source, and the energy can be captured on the sensor. So this form of energy will again be passive form of remote sensing. Why? Because you are not carrying any other source on the platform, but the target itself is behaving as a source. Okay, so we learned here that there can be reflective type of remote sensing, there can be emissive type of remote sensing. The solid red line is a reflective type of remote sensing, and the dotted red line is a emissive type of remote sensing. Also, we learned about, both of these are passive, right? But also we learned about the difference between active and passive remote sensing. So now that we learned the answers to what, why, and how of remote sensing, the next part of this class will be focusing on, number one, the properties of electromagnetic radiation. Why? Because it is the electromagnetic radiation only which is being sensed by the sensor, be it active remote sensing, be it passive remote sensing, be it reflective remote sensing, be it emissive remote sensing. It is the electromagnetic radiation which are being sensed by the sensor. So we must understand the properties of electromagnetic radiation. Number two, we will learn about how interaction takes place between electromagnetic radiation and matter. Matter here in terms of target as well as with atmosphere, which is bringing up noise in the data. So these will be the three major points which I'll be focusing on: properties of electromagnetic radiation, interaction of radiation with target, and with atmosphere. So to begin with, coming to electromagnetic radiation. So what it is, so it's a very basic fundamental concept. There are two theories in physics. One theory supports the wave nature of light. The other theory supports the particle nature of light. In the wave theory, we consider electromagnetic radiation as made up of harmonic sinusoidal waves, and this is continuously being flowing, whereas in particle nature of light, we consider the radiation as consisting of several discrete or quantized units. We call them as photons. So let me put some more time to electromagnetic radiation as a wave. So as the name suggests, it has electric fields, it has magnetic fields, and these two fields are perpendicular to each other. You can see here in this diagram, which is shown here. So if this is the electric field, magnetic field is perpendicular to it, and at every time and space, this axis represents distance or space axis, whereas you can interpret it differently in terms of time axis also. So electric field and magnetic fields will remain perpendicular to each other at all points in space as well as time, and the energy will flow in a direction perpendicular to both of these directions. So in this case, if this is your electric field, this is your magnetic field, the energy will flow in a perpendicular direction. So in this, so we have put here as electromagnetic wave is a transverse wave. So why transverse? Because it is, the energy is flowing in perpendicular direction to the oscillation of the fields. Okay, it's a transverse wave in which the electric field and magnetic field at any point and time, point here means space. So any point in time in the wave are perpendicular to each other as well as to the direction of propagation. Now there will be some terms which will be coming across very frequently in the coming course, which is lying ahead. So I'll just briefly touch upon them. So for any wave, if suppose I have drawn this kind of wave, so this represents that I have shown only one of the fields. It can be either electric field or magnetic field, but you have to interpret it in the manner that the other field is perpendicular to it and it is not shown right now. Okay, so crest is the highest point of the wave, trough is the lowest point of the wave, and the difference between, or the distance between, two identical points on the wave is called wavelength. Okay, so you can take any two identical points on the wave, but these should be consecutive, the next consecutive identical points. Then comes frequency. Now, as we understand in a layman's language also. Frequency is the number of wavelengths here, number of cycles, we say number of cycles per unit time. So here one cycle means one wavelength. So the number of wavelengths that pass a point in a set period of time is called frequency. The units of wavelength will be meters, the SI units, and frequency, the units of frequency will be cycles per second or second inverse, or in other terms we call it as hertz. Right. So how the frequency and wavelength are related? Frequency is inversely proportional to the wavelength. Okay, so putting this together in the form of an equation, we get that the product of wavelength and frequency is a constant, and this constant is the speed of light. And the value of this constant is 3 into 10 to the power 8 meters per second. Also, please mind it that light does not require a material medium for its propagation. That is why we are using light or electromagnetic radiation as a medium to carry energy or to carry the information in space-borne measurements. Any other type of energy which could not sustain in vacuum cannot be used if we are looking at space-borne measurements. Now coming to particle nature, if you want to calculate the energy of the photon, we can calculate it using this relation. That is, the energy is directly proportional to the frequency of light. So here for one photon, E is equal to h into nu. H is the Planck's constant. For if you have n number of photons, this will be multiplied with n into h into nu. So these are some basic terms which are associated with electromagnetic radiation, and finally putting it into a wave-particle duality. That is, when the wave theory is also there, the particle theory is also there, which one to take? The light exists both in the form of waves as well as particles. It has a dual nature. And this equation here, that is lambda, which is the wavelength, is equal to h by p. H is the Planck's constant and p is the momentum. This combines the two natures in one equation, and it is called de Broglie hypothesis. So wavelength is the parameter representing a wave. Okay, and momentum is related to any particle, where momentum is equal to mass into velocity, okay, for a moving particle. So, but we know that the light is not having any mass, so m is equal to 0. A photon mass is 0. So in that manner, the momentum should also be 0, but it is not so. We can calculate the momentum of photon based on its wavelength. Okay, so this is de Broglie hypothesis, which claims that all matter, not just light wave, it is applicable to all kinds of matter, has a wave-like nature and a related wavelength and momentum. Okay, so with this, we understand the basic terms associated with EMR, that is electromagnetic radiation. Now coming to electromagnetic spectrum. Because your remote sensing instrument will be sensitive to certain range of energies. Okay, it might not be sensing the entire spectrum. So we need to understand how the electromagnetic spectrum is put up. So this way, I hope all of you have an information already with you on this, where cosmic rays are having the highest energies, then gamma rays, then X-rays, then ultraviolet, then visible, infrared, microwaves, and finally radio waves. So the cosmic rays have the lowest wavelengths and the highest frequencies and the highest energies, whereas the reverse is true for radio waves. Now, where do we have our interest? For Earth observation purposes, we look mostly at visible, sometimes at ultraviolet regions also, if we are sensing the atmosphere, for example, the particulate matter. So there we look at the ultraviolet region also, but majorly for all the targets of Earth, we are looking at visible, infrared and microwave region mainly. Okay, so that is why this is highlighted. Otherwise, for extraterrestrial observations, you can go for other regions of electromagnetic spectrum as well. Now, as I said, that we will be looking at majorly visible infrared and microwave. So let's have a glance at the properties of this range of electromagnetic radiation. So the visible range ranges from 0.4 to 0.7 micrometers. You can easily recognize in different colors. But the important point here is to note that different remote sensing instruments have different definitions for blue, green, then deep blue, then red, etc. So look at the spectral range, which is defined by the data provider side, and then accordingly do the analysis. Then coming to infrared range. Now, infrared region, you need to note that it is ranging from 0.7 micrometers to 100 micrometers. However, we further divide it into two portions. That is 0.7 to 3 micrometers, and the other is 3 micrometers to 100 micrometers. Why this further differentiation is there? Because of different types of techniques involved in the remote sensing used in these two parts of spectrum of IR. That is in 0.7 to 3 micrometers. This portion we call as reflective IR, because the most of the radiation or the energy is reflected in this part of the infrared regime. So the technology which we use here is very similar to what we use for visible region. In fact, together the reflective portion, together the visible portion of light and the reflective IR, that is 0.4 to 3 micrometers, form what is known as optical remote sensing. So optical remote sensing is not only limited to the visible range. It is covering the visible range plus the reflective IR. That is 0.4 to 3 micrometers. The rest part of IR, that is 3 to 100 micrometers, is mainly emitted from the objects or re-emitted from the objects. So we do thermal remote sensing or the emissive remote sensing in this range. So we call it as thermal IR region. That is from 3 microns to 100 microns. Then finally coming to microwave range, where you will have a dedicated class on the microwave portion, but I'll be touching upon it. The range is usually about from 1 millimeters to around 30 centimeters. This covers the longest wavelengths used for remote sensing purposes. Now, this became very popular because of its long wavelengths associated with this range. These could penetrate longer distances, and these could penetrate the clouds as well, which the optical region failed to do so. So this gained popularity, but today this range is being utilized into cloudy, cloud-free, and many more kind of applications. Now, having a look at the different regions of electromagnetic spectrum which are being used for remote sensing, the next we need to learn is how to measure the radiation. So we learn radiometry. Radio refers to radiation and metry refers to measurements. So measurements of radiation. So before I go to the formal units, I would like you to introduce to solid angle. These are the angles in 3 dimensions. These are not the usual angles that you used in your geometry, where the angle is equal to arc of the circle divided by the radius. No, it is now the angle in 3 dimensions. So we call it as solid angle. So instead of the arc, it becomes the circle of the sphere. And instead of the normal angle, it becomes a cone angle. Okay, so that by definition it is, the definition of solid angle is the cone angle subtended by the portion of spherical surface at the center of the sphere. So here in this case, ds is the area which is subtended on the sphere, and d omega is the solid angle. So by definition, d omega is equal to this area ds divided by square of radius to keep it dimensionless. The units are st radian. Radian is the unit of angles in 2 dimension. St refers to 3D, so the name st radians. SR is the depiction. Now, coming to the radiometry, the very basic unit of measurement of radiation is energy. The units are joules. If we want to sense how much energy is coming in a unit time, that is the rate of change of energy per unit time, we call it as flux or radiant flux. The units will be units of energy divided by units of time, that is joules per second, which becomes watt. Now here we have added the information on time to energy. Now if I further want to know this energy per unit time is hitting at what area or is coming out from which area, so we further can differentiate this flux with respect to the surface area, and we call it as flux density. This is the rate of change of radiant flux with respect to surface area. If the energy is incident on the area, we call it as irradiance. If it is going out from the area, we call it as exitance. Okay, the units will be same for both. That is the units of flux divided by the units of area. That is your watts per meter square. Okay, so now we have added the information of time here and area here. Now, if I go by another side, this side you can see, if I want to know how much energy is coming or going in a unit angle. Okay, so we have to differentiate this radiant flux with respect to solid angle. So the rate of change of radiant flux with respect to solid angle is called intensity or radiant intensity. The units will be the units of flux divided by the units of solid angle. That is watts per steradian. Okay, and now we can move from this way or this way to add the information of all the three: time, solid angle, and area. So if I move from intensity this side, so rate of change of intensity per unit area, that is your radians. So the units will be the units of intensity divided by the units of area. Watts per steradian per meter square. So what we have done, we started with energy, we started pumping in the information on time, solid angle, and area, and we reached at different units: energy, flux, intensity, flux density, and finally radiance, which has the information on all three: time, solid angle, as well as area. So these are the commonly used terms to measure the electromagnetic radiation. Okay. Now, before we move ahead, I think we can have a 5 minutes break with a quiz to you. Number 1, is our eye a remote sensor? Number 2, what are the units of spectral radiance? Number 3, which radiometric quantity would be suitable to measure at sensor signals? And lastly, radiation of wavelength 4 microns fall in which portion of EMR? So let's take a break for 5 minutes and I'll be back with the answers to these questions and moving ahead. So welcome back. Yeah, so time to answer the questions that were raised. So is our eye a remote sensor? Yes, definitely. It's sensing the information without being in contact with the target. What are the units of spectral radiance? So we discussed radiance, and it contained information on energy, time, area, and solid angle. So that way, the units of radiance is watt per meter square per steradian, but are attached a prefix to it, spectral. So that means the energy which is measured in a particular spectral range. So C is the answer, watt per meter square per steradian per micrometers. Then which radiometric quantity would be most suitable to measure at sensor signals? At sensor signals means the signals which are reaching the sensor on the platform. So we need to gather the information on energy with respect to time, area, and solid angle also, because the sensor will have a particular field of view. So the answer will be radiance. Lastly, the radiation of wavelength 4 microns fall in which portion? It is IR. Okay, so moving ahead, coming to the next topic, which is black body. So black bodies are the idealized objects. No such object exists in nature, but these are the idealized objects that absorb and re-emit radiation in a characteristic continuous spectrum. But this spectrum is temperature dependent. How? Let us see with the help of the law, the basic law, which is Planck's law. So on the x-axis, you see that we've plotted the wavelength. On the y-axis, we have spectral radiant excitance. So it is nothing but the flux density, spectral flux density. So for a source, black body is a source. So for this source, at different temperatures, we can see the pattern. So what we see is, as we move from low wavelengths to high wavelengths, spectral radiant excitance increases, reaches a maximum, and then starts falling again. And similarly for 873 Kelvin also, it increases first and then starts falling down. Similarly for all the temperatures, you can see that the spectral radiant excitance increases with increase in wavelength, reaches a wavelength where peak emission takes place. So this peak emission wavelength is called the wavelength of peak emissivity, where the object emits its maximum. Okay, so, and then it starts falling down again. So what do we see? The other point here is, as you keep on increasing the temperature, the excitance increases at all the wavelengths. That means what will happen as you heat up the source? Number one, the excitance keeps on increasing at all the wavelengths. And number two, another interesting feature is the peak emission wavelength starts shifting towards lower wavelength side. So it's like when you heat up an iron rod. Iron rod is not a perfect black body, but still, just as an example, if you heat up an iron rod, first it becomes red. Further you heat up, it becomes yellowish. Further you heat up, it becomes bluish white. So the peak emission increases, the temperature increases, the excitance increases, and the wavelength at which maximum emission takes place, that keeps on decreasing. So this is known as mathematically Planck's law of radiation. Now, if you differentiate this law with respect to temperature, you can see that with respect to wavelength, you'll get Wien's displacement law, and which this states that the peak emission wavelength is inversely proportional to the absolute temperature. Whereas if you integrate it over the entire wavelength range, you will get excitance. Now, spectral term will not remain there because you are integrating it over the entire range of spectrum. So the total excitance is directly proportional to 4th power of absolute temperature. That means as you keep on increasing the temperature, excitance, total excitance increases. And if you double the temperature, the spectral excitance will become 16 times 2 to the power 4 times. Okay, so these are the two corollaries of Planck's law, where after integration you get Stefan-Boltzmann law, and after differentiation you get Wien's displacement law. But that states good for a black body, right? But what about the real objects, real sources, real targets? How close a real body is to a black body? Now, to tell this, we have a figure of merit, which is called spectral emissivity. So spectral emissivity is the spectral excitance of the real object divided by spectral excitance of black body at same temperature. Okay, so if you have a black body itself, this emissivity will be 1. If you have a perfect reflector which does not emit anything, so then in case of that, your emissivity will be 0. Real objects will always have emissivity values ranging between 0 and 1. If the value is close to 1, for example, that's for water. Water is a good absorber, good emitter, right? For metals, this emissivity will be low because metals reflect more and emit less, right? So this parameter tells you about the emission properties of objects. Now coming to electromagnetic radiation with matter. Now, there are two instances. Either this interaction takes place at the boundary of two surfaces, or this interaction takes place within a medium, a single medium. At the boundary of two surfaces, we all have learned part of the energy will be reflected and part will be refracted or transmitted. Within a single medium, the two processes again happen: absorption and scattering. Scattering is the redirection of light, and absorption is this the particles absorb the energy, and then further this raised energy is re-emitted, right? So coming to the interaction of radiation with targets. So we know that I have stated already that the total energy will be partly reflected, partly absorbed, and partly transmitted. So this is your this brings to you the law of conservation of energy, and correspondingly Kirchhoff's law of radiation. If you can divide both sides by the total incident energy, that is EI by EI is equal to ER by EI, where EI is the incident energy, plus EA is divided by EI, plus ET divided by EI. So this gives you 1 is equal to reflectivity plus absorptivity plus emissivity, transmittivity. Right? So this is the Kirchhoff's law of radiation. Now coming to the interaction processes. If we are interested in the reflective type of remote sensing, I'm particularly talking about optical remote sensing, because thermal remote sensing and then microwave remote sensing will be discussed and dealt with separately. So I'm discussing only the optical remote sensing from here onwards. We are interested in the reflected portion of electromagnetic radiation reaching the sensor. So we would like to understand the reflective properties of targets. There are broadly two types of reflections. One is specular and the other is diffused. Specular is mirror-like. That means the angle of reflection will be same as the angle of incidence. Whereas in diffused reflection, if the incident light is coming in one direction, the reflected light will go in different directions. If the perfectly diffused reflector, if the incident light is coming at one particular angle, it will be reflected at all different angles. Okay. So an example is shown with the help of this diagram here. For optical remote sensing, the smooth road is behaving as specular reflector, whereas tree canopy, with leaves oriented in different directions, behave as a rough reflector, and diffused reflection can be seen. Now, how to tell whether the surface is rough or smooth? Okay, not just by having a look at what kind of texture the surface has. The same surface can behave as rough or smooth depending on two conditions. Number one, what is the average undulation of the surface and what is the wavelength of interaction. Okay, the same surface with same average undulation can behave differently at different wavelengths. It may become rough in certain wavelength range and it may become smooth at certain other wavelength range. Now, for this, mathematically, the criteria, a rough criteria is H is where H is the average undulation. If H is greater than lambda by 8 cos theta, where theta is also one of the factors, which is the angle of incidence. So the same surface, if you look here or here or here or here at different angles of incidence or observations also, then also you will see that the surface might behave its nature from rough to smooth. Okay, so you can test the smoothness or the roughness of the surface and thereby whether there will be specular reflection or there will be diffuse reflection using Rayleigh's criteria for rough surface. Now, coming to another topic, which is very much of interest to you for all the interpretation classes and all the further analysis classes with spectral signatures. So as the name suggests, it is a unique identification for the feature. So in optical remote sensing, it is given by the variability of spectral reflectance with respect to wavelength. So you can see here I've plotted the typical spectral signatures for vegetation and for two types of soil, dry and wet, and then two types of water, clear lake and turbid river. And you can see here that different types of features behave differently in different wavelengths ranges. So you can identify different features based on their spectral signatures. The details of the different spectral signatures of different objects will also be covered in the forthcoming classes, where you will learn why vegetation has a very high reflectance in near infrared range, why there are three major dips you can see in vegetation also and in soil also, why water only has very high reflectance, very low reflectance in the very shorter wavelength ranges, and then in the infrared range its reflectance is near zero. Why? The answer to why of all these questions will be covered in the forthcoming classes, especially in your visual interpretation and spectral signatures, where you will learn why different features will have different types of signatures. But you need to understand here that different features in remote sensing can be identified using their spectral signatures, right? And finally, coming to interaction of radiation with atmosphere. As I said, we don't want this signal to be altered, but what to do? Atmosphere is always there and it will always perturb the signal. Now, how much it will perturb will depend upon which wavelength and which particles, which wavelength of electromagnetic radiation and which particles present in the atmosphere are going to interact with. Majorly, as I said, there will be absorption and scattering. So due to absorption, what happens is certain wavelength regions are not allowed by the atmosphere due to presence of certain gases. For example, ozone absorbs ultraviolet radiation, so it will block this type of radiation to come and to go through, okay, both while incoming as well as while outgoing. So there are different types of gases present in the atmosphere, and these gases absorb the different wavelengths of energy, and the atmosphere will not remain transparent to all those regions of spectrum. So whatever regions will be allowed by the atmosphere, regions means electromagnetic regions, whatever spectral range, whatever wavelengths will be allowed by the atmosphere, there only you can be able to do remote sensing for Earth targets. Because for sensing the Earth targets, the signal must be able to come to the target and to go from the target. Okay, so here in this diagram, you can see that on the x-axis you have wavelength, and on the y-axis you have transmission. And there are several atmospheric windows. Windows means those regions where electromagnetic radiation is passed without much attenuation. Okay, the attenuation is low. Around 90, more than 95% of the signals is usually transmitted. Even 90% transmitted is also a atmospheric window region. So you can see the shaded regions are all atmospheric window regions. So what absorption has brought to us is we are left with only the atmospheric windows to do the remote sensing for Earth targets. Due to scattering, what happens now? Different types of scattering may happen. For example, if you look at the central one, the light is coming in this direction, and this particle is redirecting it into equally forward and backward directions, right? So half of the energy is transmitted in the forward and half of it is transmitted in the backward direction. This kind of scattering is called Rayleigh scattering. Another type of scattering, can look here, is when most of the energy is transmitted in the forward direction and less in the backward direction. So such kind of scattering is called Mie scattering. And then we have these two types of scatterings. Rayleigh and Mie are dependent on the wavelengths. So we call them as selective scatterings. Shorter wavelengths are scattered more in Rayleigh and Mie, whereas we have another type of scattering also, where the scattering is independent of wavelength. Whatever wavelength strikes the particle, all are equally scattered. So we call as non-selective scattering. So I put it into a table. For Rayleigh and Mie, wavelength dependency is lambda to the power minus 4 and roughly here to the power minus 2, whereas it is a variable range. So shorter wavelengths like blue will be scattered more in Rayleigh than red. Similarly for Mie also, but the amount of scattering that blue will suffer due to Rayleigh scattering will be more compared to Mie. Okay, and most commonly found Rayleigh scatterers are air molecules, the gaseous molecules. Mie scatterers are usually the aerosols, and non-selective scattering are usually the cloud droplets. Right. So what atmosphere has done to remote sensing? Due to absorption by the atmosphere, we are left with atmospheric windows. And due to scattering, there is modification of spatial as well as spectral distribution of incoming and outgoing radiation. Okay, and also more turbulence means resolution will be limited. So scattering introduces poor contrast, or it affects, or it brings haziness in the image. So with this, I'll summarize what we learned. We started with the overview, what, why, and how, and then we moved on to electromagnetic radiation concepts, radiometry, and finally to the interaction mechanisms between radiation and target, as well as radiation and atmosphere. So with this, I stop here, and with 2 minutes break, we'll quickly come back to take up if there are questions with you and further interactions. Thank you.